Hello everyone, this is Group 52. The topic we chose is the homomorphic encryption in literature track, and we intend to study its use in cloud computing. An encryption is homomorphic if the encrypted result of computation on two plaintexts can be directly calculated by applying the same computation on their corresponding ciphertexts. The computation here can be addition, multiplication, or exclusive OR. This feature greatly facilitates the use of homomorphic encryption-related schemes in cloud computing, as operations like search and manipulations of confidential data can be done on the cloud without full decryption. In the following section, we will introduce three popularly used encryption algorithms on cloud computing and make comparisons to prove why homomorphic encryption is the best choice.
Attribute-based encryptions allow secure one-to-many communications according to their attributes. Data owner receives the public key to encrypt the data along with the attributes. Data users gets the secret key from authority and decrypts the data. Attribute-based encryptions only satisfy basic requirements of security. Data confidentiality and collusion resistance are satisfied, because ABE uses attributes in the user's secret key to match the attributes in the encrypted data, and each attribute has public key, secret key, and a random polynomial. Requirements such as scalability is not satisfied. Space cost and time cost is very high, as data owners store the public key for encryptions and the data users store the secret key for the decryptions. Pair operations is costly.
RSA can also be used in the cloud computing. In general, the private key in the RSA system should be known only to the user who owns the data, and the public key is known to the cloud server. For security analysis, it has a good security performance. The difficulty of cracking RSA is similar to making large numbers of factorization, which is a hard problem for now. However, this security is for users only. It cannot provide any security for the cloud means. RSA naturally has a collusion resistance, since only one user has a private key. It is also a non-scalable algorithm in the cloud computing, since it requires many computational sources, which we'll talk about next. RSA is very slow in processing. It's mainly because of long-length prime generations. In addition, RSA maps all text into integers. For the space cost, the cloud side also needs to download the data first and decrypt it, which requires more space.
A homomorphic encryption can be classified into two categories. Partially homomorphic encryption can carry out a certain type of operation on ciphertexts without decryption, but it is not sufficient in common areas. The following analysis is discussed upon fully homomorphic encryption, which is universally homomorphic for all computations. The results of calculations can be provided without knowing the raw data, so the confidentiality of data is kept from the cloud provider. Homomorphic encryption would be susceptible to a collusion attack, but certain schemes can keep it collusion resistant. And homomorphic encryption is scalable when decrypting because it allows a limited number of computation operations to be performed. A fully homomorphic encryption has a high ciphertext expansion rate, big key size, and long key generation time, and its bootstrapping operation is costly. But the current implementations using GPU and FPGA improve this circumstance.
Here comes the comparison part. Even though all three algorithms are used in different cases, they provide different levels of security. Homomorphic encryption has the highest level of security among them, since the data stored in the cloud is ciphertext. There are also evidence that homomorphic encryption systems are used to perform operations on encrypted data without knowing the private key. Things are also conversely in the RSA case. Users are the one who owns the private key to decrypt the data. This means that the data is encrypted in the cloud and stored in the plaintext form. As for ABE, the algorithm has a lower level of security compared with the other two algorithms. One of the papers states that it only satisfies the basic requirements of security, which is data confidentiality and collusion resistance. Scalability is also one of the advantages that cloud computing over traditional computing. However, only homomorphic encryption carries on this advantage among all three algorithms. The fully homomorphic encryption operation roughly corresponds to bitwise operations, which are allowed an unlimited number of times to be performed. For the rest two algorithms, neither RSA nor ABE is scalable because of their own constraints. ABE is limited to a fixed number of attributes so that fewer users' collaborations can happen. In terms of RSA, RSA decreases linearly in the number of users and ciphertexts. Since RSA needs to choose two long-length prime numbers as its key, it's infeasible for the computational resources, which is the reason why it's not scalable. Another important factor in the encryption algorithm related to security is collusion resistance. It's one of the few security schemes that ABE has. It's impossible for users to combine the data they have and violate system security since each of them has different features, which means keys. Similar principle applied to the RSA algorithm. Only the owner itself has the private key, which makes it collusion resistant naturally. However, among all three algorithms, only the homomorphic encryption has a little issue with it, but it can be fixed with some specific mechanism that had been introduced before in the previous section. In summary, homomorphic encryption has an overall better security comparing against the other two commonly used algorithms.
Perhaps cost and space complexity are always the disadvantage of cryptography. Compared with others, homomorphy is still the good choice based on cost and space analysis. While RSA encryption is caused by data processing speed that cannot be measured, RSA still takes less time to run compared with ABE. Because its modular exponentiation calculations is much lighter than pairing operations used in ABE. Therefore, in cloud computing, homomorphic encryption is fitting choice because it can process data in an encrypted form, which will provide faster processing speed. In homomorphy, cloud service providers support encrypted storage of documents, but want to enable users to edit their documents without decrypting them first. Compared to RSA and ABE, you need to download the data and decrypt the data first. Especially ABE has a quite high cost of space, because the length of user secret key and ciphertext are corresponding to the numbers of attributes. Therefore, while there are millions of users in cloud, RSA and ABE are not the good choices.
In this presentation, we discussed the three commonly used encryption algorithms on cloud computing, and we have compared them through the aspect of both security and performance to show that a fully homomorphic encryption algorithm is the best choice when it comes to cloud computing. For the next stage, we will further study its authentication property, some other related schemes that utilize this algorithm, and its optimization processes. As the new avenue of targeting hardware or GPU technology for optimized fully homomorphic encryption architectures looks very promising and brings the possibility of real-time implementations a step closer. This is the end of our presentation. Thanks for listening.